Hello and welcome to the session. I am Dr. Akshay Kumar from School of Computer and Information Sciences, IGNOU, and today I'll be discussing with you about two main concepts. One is called Principle of Optimality, and then I'll be discussing with you one example of Principle of Optimality called matrix chain multiplication. What is the Principle of Optimality? There are two principles. It basically defines the components of globally optimum solution. Okay, so if there is a global optimal solution, then each part of that particular solution or each component of that particular solution, that should be optimal. That is what is the principle of optimality. And one of the common example of that principle of optimality, the problem which follows principle of optimality, is the shortest path algorithm. Okay, now shortest path algorithm, basically if I want to define shortest path from a source A to a destination B, then it may consist of A, x1, x2, so on till xn and b. So suppose this is the shortest path between two destinations, right? So it's the shortest path from node A to node B in a graph. Then portion of graph, any portion of the graph, xi to xj, which may be from x2 to x5, let's say, okay, on that path, so any portion xi to xj on that path is shortest path from xi to xj. So that is what principle of optimality says, that if A to B and there is a small path short path between x2, x3, x4, then that path x2, x3, x4 will be shortest path also between x2 and x4. So with that, a problem has an optimal substructure. So this is called an optimal substructure if an optimal solution can be constructed efficiently from optimal solution of its subproblems. In a sense, if a particular problem follows the principle of optimality, then you can basically try to find out the optimal subproblems to the main problem and find the solution to this big problem by finding the solution to the subproblems. Okay, so this particular principle of optimality, if a particular situation problem is satisfying this particular property, then we can use dynamic programming for such situation. So what is dynamic programming? So dynamic programming is to develop a mathematical notation that can express any solution and sub-solutions of a problem. Okay, so so if I want to solve anything by dynamic programming, so we will be using solutions and sub-solutions. So we need that the problem statement or problem proves the principle of optimality. It should hold for that particular problem. Okay, then develop a recurrence relation that relates a problem to its subproblems, okay, and identify the terms that signifies the final solution. In recurrence relation, you always do this particular thing, and there has to be a final solution in recurrence relation, right? So you will be first identifying the terms and its subterms, okay, and there has to be a final solution, a term specifying the final solution. And then you will be writing an algorithm to compute the recurrence relation. So you identify, okay, compute the recurrence relation. How do you compute it? And when the principle of optimality holds, dynamic programming based solutions are guaranteed to yield the optimal solution. And in such cases, no proof of optimality is needed. Okay, you should know that this particular problem satisfies the principle of optimality. Now, matrix multiplication is a very interesting situation which many a times tries to satisfy, okay, the principle of optimality as far as computation of multiplications are concerned. Now, what is a matrix multiplication? You all know, but let us try to define matrix multiplication from the context of what we will be using and what we will be defining when we will be discussing the dynamic programming solution to matrix multiplication. So, a matrix multiplication is a binary operation. If you are trying to multiply two matrices, then you have just a binary operation. You are multiplying matrix A with the matrix, another matrix B. All right. So, it can be, very important point here is that matrix multiplication can be performed when two matrices are conformable. Conformable means if matrix A and B are of order P cross Q, suppose A is of order P cross Q and B is of the order S cross T, okay, then if I want to define A cross B, that is A matrix A is multiplied by with matrix B, it will happen when Q is equal to S, all right. Q is equals S. And if you want to define B cross A, B multiplied by A, then T, right, because it is S cross T and this matrix is to be multiplied with P cross Q. So, this T should be equal to P. That is what is the requirement when you want to multiply two matrices. The important point about matrix multiplication is that matrix multiplication is associative. That is, if AB and C matrices of order M cross N, N cross P and P cross Q, so these are the three matrices, then AB multiplied by C, that is you are multiplying AB first and then the product is multiplied by C, okay. So, in a sense you will be, when you do AB multiplication, you will be producing a matrix of size M into P and then this matrix will be multiplied with P cross Q to produce a matrix of M into Q size, all right. And if you multiply A with product of BC, then first you are multiplying BC. So, what you are producing? N into Q as the product. So, BC will be a matrix of the size N into Q. And if you multiply it with M into N, so once again you will be producing an M cross Q. The size of those both the matrices are same. In addition, all the elements which you will be producing will also be the same. So, this particular property, that associative property as far as matrix multiplication holds. However, it is a very interesting situation where matrix multiplication is defined to be not commutative. Why? Because if AB has dimension M cross N and N cross P and M is not equals to P, it's not necessary that M is equal to P. So, what you can say, you will be able to define AB because this particular dimension is the same, okay. For conformable matrices, obviously this both should be the same and they are N, so obviously they are the same, okay. So, we will be producing a result, M cross P result, all right. However, BA cannot be defined since M is not equals to P. Therefore, AB is not equals to B cross A or B multiplied by A. So, that is a typical property. That means, if we are multiplying three matrices, then that particular chain has to be maintained. Okay, suppose that is, if you are doing multiplication of ABC, then you can do anyway. both the matrices, both the multiplications are the same, producing the same results. But in a sense, you cannot change the order. You cannot say that C will be multiplied by AB. Order has to be like that. Alright. So that is one of the main requirements when you are doing the matrix multiplication. Let us try to understand matrix multiplication with the help of a very simple example, how you multiply this the two matrices. So now in order to do that, we will also try to ascertain some basic facts about matrix multiplication. So what we want to ascertain is, suppose I am multiplying two matrices, okay, how many multiplication would be required? Okay, scalar multiplication. Suppose matrix is it's basically a group of scalar values. Huh? So these are my two matrices, right? This matrix is of the size 3 cross 2. So this is A is of the size 3 cross 2. And my matrix B is of a dimension or order 2 cross 2. Okay, so 2 rows and 2 columns. All right. It has 3 rows, 2 columns. That's why it has an order of 3 cross 2. So how do you multiply two matrices? That is the first row multiplied by the first column to produce the first element of the resultant matrix. So 1 into 1 plus 2 into 2. All right. So that is what you will be getting. Okay. As the next 1 into 2 into 3 into 4, the second column you will be getting. Right. Okay. Then the second row's element. Okay. So second row will be multiplied by with the first column. So 3 into 1. Okay. Multiplied by 4 into 2. Likewise, 3 into 3 plus 4 into 4, and like that. All right. So this is how the matrix multiplication, or the general term of matrix multiplication, goes, and you are just adding these elements to produce a final output. So you can verify this particular output. Okay. Now our concern is how many operations are required in this. So the costly operation is the scalar multiplication. And how many scalar multiplications we are doing? If I see 1, 2, 3, 4, 5, 6, and once again 6 plus 6, so we are requiring 12 multiplication. How can we ascertain these multiplication? From the order or dimension of the matrices. So we are doing the 3 cross 2. So suppose I call it M, I call it N, and N into P, which is 2 cross 2. So the number of multiplication required will be M cross N cross P. Okay. Why? Because that's how the multiplication is going, equals to the number of rows multiplied by number of columns. So that is how you will be able to determine. So in this particular case, M is 3, N is 2, and P is also 2. So the number of multiplications which will be required will be 3 into 2 into 2, which are 12. So this particular statement is very, very important. That is, if I am multiplying two matrices of size A and B of an order M cross N and N cross P, right? So my result, size of my result is going to be M into P, M cross P, and the number of multiplication, which is the costly operation, they will be M into N into P. These many scalar multiplications will be required. Plus, yes, there will be addition operations also, 6 addition operation, which is basically equals to 3 into 2, right? This 3 and into 2, but they are less in comparison to multiplication and less costly in comparison to multiplication. So our objective will be to minimize the multiplications. Okay. Obviously, we cannot minimize the multiplications when we are multiplying just two matrices, right? So they are going to remain like that. But then when we are doing chain matrix multiplication, a number of matrices are being multiplied. our objective is going to be minimizing that particular overall multiplication. Okay. So, matrix multiplication, how this particular operations can be performed. So, matrix multiplication is associative, we have already discussed about it, and the scalar of matrix multiplication may vary significantly depending on how we pair the matrices and their product matrices to get the final product. Now, that is very, very important. And this particular statement, let us prove this particular statement with the help of an example rather than mathematically. Okay, so let's consider three matrices of the order. A is of the order 100 into 10, B is of the order 10 into 20, and C is of the order 20 into 5. And we want to determine the product A multiplied by B multiplied by C. First thing first, are these matrices conformable? Let's see. This particular dimensions matches this. So, it is that is A and B are conformable. What about B and C, right? The 20 and 20. So, these two are also conformable, right? So, these A, B, C are conformable matrix as far as multiplication is concerned in that particular order, A, B, C. However, we can multiply it in a way, first we can multiply AB and the product of AB, then we multiply with C. So, if we multiply AB, it will require how many computations? Well, this is 100 into 10 and 10 into 20. So, you are multiplying these two matrices. So, our equation was M into N into P. What is the value of M in this particular case? 100. What is the value of N in this particular case? 10. What is the value of P? 20. So, the number of operations which will be required, because we are multiplying two matrices 100 into 10 with 10 into 20. So, we will be requiring these many multiplication, which is 100 into 10 into 20, which is 20,000. And the order of A multiplied B is going to be just 100 into 20, these two, M into Q, M into P, last two elements, right? So, this will go, so this is the order of the resultant matrix, which is AB. Okay, so now we have got AB, okay, with a dimension of 100 and 20, alright. So, now we will be multiplying it with C, which has an order of 20 into 5. So, how many multiplication then will be required? 100 into 20 into 5, alright. So, 100 into 20 into 5, these are 10,000 multiplication, alright. So, overall, when we multiply this, our order is going to be 100 into 5, that is going to be the order of result. And how many multiplications are needed? 20 plus 10. So, overall 30,000 scalar multiplications are needed in this. If we sum these two up, we will get the number of multiplications which are required if we multiply three matrices A multiplied by B multiplied by C, as first AB is multiplied and then the result is multiplied with C. Is there any other option? Yes. The second option is we first multiply B with C and the result of that is multiplied, that is A multiplied by result of B multiplication C. So, how many computations would be required for B into C? Now, what is the dimension of B? 10 into 20. What is the dimension of C? 20 into 5. So, the multiplications required will be 10 into 20 into 5. Okay, these are just 1000 computations. Alright. And the order of BC is going to be obviously first dimension and the last dimension. This is going to be 10 into 5. Alright. So, the ABC will require 100 into 10 into 5. Okay. And then when we multiply with A, B and C, what we will be multiplying? 100 cross 10 matrix, which is A, with result BC, which is 10 into 5. So we will be requiring 100 into 10 into 5 multiplications, which are 5000 multiplications. Alright, so if I sum them up, only 6000 scalar multiplication. In this particular case, we were requiring 30,000, here we are requiring 6,000. There is a vast difference. Alright, so matrix chain multiplication is a very important problem. This particular point proves that. Okay, so given a sequence of conformable matrices for multiplication, select the optimum pair of matrices in every step so that overall cost of multiplication is minimal. Okay. So for conformable sequence of n matrices, different ways of selecting matrices for multiplying grows exponentially as number of matrices grows. And remember one particular thing, the problem is not actually performing the multiplication. You are not actually performing the multiplication. But what you are deciding, the order to perform the multiplication. Whether first A multiplied by B is to be performed, followed by C, or first B into C is to be performed and then A is to be multiplied with the result BC. Like that we need to define if the sequence is very large. For example, consider a conformable multiplication sequence of now 4 matrices. Okay. Now fully parenthesizing this means that we are basically deciding about the number of multiplications on that. Okay. So the first way will be, if I simply multiply CD, then the result of CD, B with the result of CD, and the result of BCD with A. So A with BCD result, like that. Sequence cannot change in that. Otherwise, conformability will break, and since they are not, as a property is not valid, so it's not going to work. Okay. So A, BC, D, another way. A, BC, B. This is now, first we are performing BC, then we are multiplying BC with A, and then overall product is multiplied by D. Then AB and CD separately. Okay, like then AB with C and D. Now you can see the number of different multiplications. When we were having just 3 matrices, there were only 2, but now they have grown exponentially. They have grown to 5 multiplication. So if we move to 5, once again they will grow exponentially. So large number of multiplications are going to be required. So how to decide which of these multiplication is going to be minimal? We are not multiplying the matrices. We are just deciding this parenthesization, that how the multiplication is to be performed. And that is the problem of matrix chain multiplication. Alright, so the problem, let us formally define the problem. How do we parenthesize a chain of matrices to minimize the cost of evaluating the product? So what is the solution? Use the dynamic programming approach to determine how to optimally parenthesize a matrix chain using the following steps. Characterize the structure of optimal solution. We'll try to characterize it. Recursively define the value of an optimal solution. Compute the value of an optimal solution and construct an optimal solution for the computed information. We'll do 2 operations in this session and remaining in the next session. So first is the structure of optimal parenthesization. So optimal parenthesization of matrix chain A1 ... AN. So it must break the product into 2 expressions, each of which is parenthesized or is a single array. So it will be an expression or it will be a single array, so the multiplications are possible. So assume to this particular break occurs at position K. In the optimal solution, the solution to the product A1 to AK must be optimal. Okay. Otherwise, we must improve A1 to AN by improving A1 to AK. So this is the optimal that is the principle of optimality is being followed by it, but the solution to A1 to AN is known to be optimal, therefore A1 to AK has to be optimal, and if it is not optimal, this is a contradiction, right? Therefore, the solution to A1 to AN is known to be optimal, then A1 to AK multiplication and AK plus 1 to AN must be optimal. If they are not, then we can find a better solution, right? So that is not optimal anymore, right? So this is proof by contradiction. So this problem exhibits the principle of optimality. So first point, whenever you want to apply the dynamic programming, is to prove the principle of optimality. The optimal solution contains the optimal solutions of two subproducts. Okay, thus we can do the optimal this dynamic programming. Next is going to be, we are going to find a recursive solution. So pick a subproblem of determining the minimum number of parenthesizing. So A1 multiplied till A plus 1, I plus 1 and AJ. So suppose this is the place where we are trying to break it. Okay. So terms, what terms we will be using? Mij is the minimum number of scalar multiplication needed to compute the matrix A, I till J. Okay, so this is already known, and the lowest cost to compute A1 to N would be M1N. So this is what we will be discussing in more details, but if I can define MII, if I am trying to multiply matrix with itself, right? So it is 0 because we are not, it is a singleton matrix, right? When I equals to J. This is a trivial problem of this particular solution. So whenever you are trying to do matrix multiplication, there has to be a trivial problem. So what you are trying to do? You are trying to break the problem into two optimal problems. And those two optimal problems last, or the minimum case is going to be when matrix is a singleton. Okay, so an example here is, if I have A1, A2, A3, A4, A5, which are conformable multiplying matrices, and I have to determine product A1 multiplied by AJ till AJ, A5. So we have to multiply all these matrices. How we are going to do it? Okay, so the recursive solution is going to be, the optimal solution must break at some point k, with k is less than greater than equals to I and less than j. Each matrix AI is of the size pi minus 1 into pi. So this is how we are going to recognize a matrix. Two dimensions are there. So first dimension is going to be 1 less than that. Okay, so this is very, very important. We will handle this as a case, and computing matrix multiplication of AI to AK and AK plus 1 to J takes what is the size being taken? P, the dimension of this is going to be I minus 1. Okay, the dimension of here is K. So I minus 1 into K, so that is Pi minus 1 into Pk into this final dimension is going, this is going to be K into J, right? Because 1 minus 1 less than that, so it is going to be Pi minus 1 Pk into Pj scalar multiplications. And this we will be finding out overall with, if I have multiplied two matrices, let's say Ai to K, AK plus 1 to J, okay, then Mij is going to be Mik, whatever is the already computed number of scalar multiplication, whatever are the already computed scalar multiplication of the other part. So scalar multiplication of both the parts, and then multiplying these two matrices. So cost of multiplication of these two matrices, that is what is being discussed. So this is a typical example. So let us try to summarize what we have tried to cover in this particular session. In this session, we have tried to define the problem of the principle of optimality. Okay, it's not the problem, it is the principle of optimality which we have defined. Okay, And dynamic programming requires the problem to show principle of optimality, which is components of globally optimum solution must be trivial or optimum by themselves. And the problem of chain matrix multiplication determines it's basically to determine the sequence in which chain of matrix multiplication should be performed. This is a typical example which shows principle of optimality and should be solved with the help of dynamic programming. We have initiated the problem. Let's solve an example of this particular problem so that you can make out what do we mean by M's, what do we mean by different terms in this particular problem in the next section. With this, we end this particular session here. Bye.